Right now, above the stretch of ocean between the coast of Brazil and the coast of Namibia, there is a hole in the sky. Not a hole in the atmosphere, a hole in the invisible field that has stood between every living thing on this planet and the raw radiation of space for billions of years. You cannot see it, you cannot feel it. If you flew a commercial jet through it this afternoon, you would notice nothing at all. No turbulence, no flicker in the cabin lights, nothing. But almost every machine humanity has ever sent up to check on that hole has come back scarred, and at least one of them came back dead. In 2016, a Japanese X-ray observatory named Hitomi passed through it, lost control of its own orientation systems, and by the time anyone on the ground understood what was happening, the spacecraft had already spun itself to pieces. That hole has a name. Scientists call it the South Atlantic Anomaly, and it is not sitting still. It is spreading. It is deepening. According to the satellites built specifically to watch it, it has already grown by an area nearly half the size of continental Europe since 2014. And on almost the opposite side of the same weakening magnet, something else has been happening. Earth's magnetic North Pole, the actual point your compass needle hunts for, picked up its feet and started sprinting toward Siberia at a pace nobody alive has ever recorded before. Two separate symptoms, same failing organ. In the next stretch of this story, I'm going to show you exactly why both of these are happening at once, deep inside the planet, roughly 3,000 kilometers under your feet, and the part almost nobody outside a handful of geophysics labs is talking about out loud. What a thinning shield actually means for the satellites overhead, the aircraft in the sky, and the power grids we have built without ever really planning for the sky to change. This story is still being written. New readings come down from orbit every single month, and some of them have already forced scientists to tear up models they trusted only a few years ago. So if you want to be here when the next one lands, when an agency has to rewrite a map a full year ahead of schedule because reality moved faster than the paperwork, subscribe now, because that is exactly the kind of signal this channel exists to catch early. Tell me where in the world you're watching this from, and whether the northern lights have started showing up somewhere they never used to, over your town, your coastline, your particular patch of sky. For most of human history, the compass was treated less like an instrument and more like a small, obedient miracle. Sailors trusted it the way you trust gravity, completely, and without asking why it worked. There is a superstition, recorded as far back as the Roman writer Pliny, that eating garlic near a compass could ruin it, could somehow poison the needle's loyalty to the north. That belief dated back to Pliny, and even after William Gilbert disproved it in 1600, there were reports of helmsmen on British ships being flogged for eating garlic. Think about that for a second. Grown men, professional navigators responsible for hundreds of lives, were being punished over onions, because the alternative explanation, that the compass itself might simply be wrong, was almost unthinkable. It took a London physician named William Gilbert to finally ask the right question. In 1600, in a dense 6-volume treatise called De Magnet, Gilbert made the claim that the Earth itself works as a giant magnet, with its own magnetic field pulling on every compass needle on the surface. He built a small magnetized sphere he called a terrella, his own miniature Earth, and walked a tiny needle around its surface, watching how it dipped and swung and pointed, proving on a tabletop what sailors had been trusting blind for centuries. It was a genuine breakthrough. It also, quietly, planted a problem that would take 400 years to fully unravel. If the Earth is a magnet, and the needle is only doing what magnets do, then the needle isn't pointing at true north at all. It's pointing at wherever the magnet's north happens to be standing at that particular moment in history, and that spot moves. Sailors had already stumbled onto this the hard way, decades before Gilbert ever picked up a lodestone. By the 15th century, navigators crossing long distances noticed their compasses drifting off from true north by different amounts in different places, a gap that came to be called variation or declination. Nobody fully understood it. Mapmakers began sketching it anyway, because ignoring it was getting people killed. In 1698, and again the following year, the astronomer Edmund Halley, the same Halley the comet is named for, sailed the South Atlantic specifically to measure this drift, and in 1701, he published a chart of the whole world, showing the magnetic variation as it had been measured that year. It was, in effect, the first weather map ever made of an invisible ocean of force nobody could see, only infer. Here's the part that should stop you. This wasn't an academic curiosity. People died over this. In 1707, 4 Royal Navy ships wrecked off the Scilly Isles, and the disaster, which killed roughly 2,000 sailors, helped trigger the Longitude Prize in 1714, one of the most famous scientific bounties in history, aimed at solving exactly this kind of navigational blindness. And even with Halley's chart circulating, plenty of captains simply didn't bother to apply the correction. Mariners often ignored variation, or were simply ignorant of it, and ships and lives were lost as a result. Picture the weight of that. An entire crew trusting a needle that was quietly, methodically, lying to them by a few degrees, just enough, over a long enough voyage, to put a hull onto rocks that should have been miles away. The compass, in other words, was never actually lying about where north was. It was telling the truth about a north that never stays put. And nowhere was that truth stranger or harder to pin down than at the pole itself. In 1829, a British naval officer named John Ross led an Arctic expedition aboard a small ship called the Victory, funded by a wealthy gin distiller, into the ice north of Canada. His nephew, a young commander named James Clark Ross, went with him. During that expedition, on the 1st of June 1831, James Ross determined the location of the North Magnetic Pole on the Boothia Peninsula. He didn't guess at it, he measured it, using an instrument called a dip circle, essentially a needle mounted so it could swing not side to side, but straight up and down, tracking the angle at which Earth's field dove into the ground beneath his boots. When the dip circle registered a reading of 89 degrees and 59 minutes, almost dead vertical, Ross knew he was standing on the magnetic pole itself, 1/60th of a degree short of straight down. His charts placed him at roughly 70 degrees north and 97 degrees west, a spot of frozen tundra that, for one morning in 1831, was the single point on the entire planet where a compass needle simply gave up trying to point sideways at all. Ross had no way of knowing it, but he had just taken a single photograph of something that never stops moving. For most of the 4 centuries before his expedition, geomagnetic records suggest the magnetic North Pole crept along at roughly 10 kilometers, about 6 miles a year. Slow enough that a mariner's grandchildren could still trust the charts their grandfather had used. That was the whole point of Ross's measurement. Pin the pole down, publish it, and sailors from Liverpool to Bombay could correct their compasses against it for a generation. Nobody expected the pole to eventually get up and run, but it did. Sometime around the 1990s, the wandering turned into something closer to a sprint. By the 2000s, the pole was accelerating to a record 55 kilometers, about 34 miles a year, tearing across the Canadian Arctic and out over open ocean, heading, unmistakably, towards Siberia. Kieran Began, a geomagnetic specialist at the British Geological Survey, put it about as plainly as a scientist ever puts anything. The movement since the 1990s is much faster than at any time for at least 4 centuries, and researchers still don't fully understand the changes deep in the core that are driving it. Since Ross's original fix, the pole has now covered something like 2,250 kilometers, roughly 1,400 miles, from its original position in northern Canada, more distance than the entire width of a continent, wandering across the top of the world like a compass needle with a mind of its own. It has slowed a little from its most frantic sprint. Over the most recent 5-year stretch, the pole's pace has eased to around 35 kilometers, about 22 miles a year, still triple the speed of anything recorded before the modern era, still heading towards Siberia, still refusing to sit still long enough for cartographers to relax. The organizations responsible for the official model of Earth's magnetic field, the kind of model loaded silently into every smartphone, every aircraft navigation system, every ship's electronic chart, have had to respond in a way that tells you everything about how seriously this is being taken. They pushed their scheduled update a full year ahead of time because the pole was moving too fast for the old model to stay accurate, until its planned expiration date. A compass, in the end, was never a liar. It has simply always been an honest witness to a moving target, and lately, that target has been running faster than the instruments meant to track it. But the racing pole, dramatic as it is only the visible tip of something far stranger. Because while the compass over the Arctic was picking up speed, something entirely different, and, in its own way, far more alarming to the people who watch this planet's magnetism for a living, had already been quietly opening up over the skies of South America. It had been there, largely ignored, since the very first days of the space age, and it was about to start breaking things. To understand what was opening over Brazil, you have to go back to the dawn of the satellite era, to a tiny American spacecraft called Explorer 1. Explorer 1 launched on the 31st of January 1958 and revealed that Earth is surrounded by intense regions of trapped radiation, vast, invisible belts of charged particles, corralled by Earth's magnetic field the way a fence corrals cattle. Scientists name them the Van Allen belts, after James Van Allen, the physicist whose instruments made the discovery. It was one of the first great triumphs of the space age, proof that the planet wore an invisible coat of captured radiation nobody had ever detected from the ground. Here's the detail that should have set off alarm bells immediately, and did eventually. That coat isn't even. Earth's magnetic field isn't a perfect symmetrical bubble centered neatly on the planet's core. The point where Earth's magnetic axis and its rotational axis actually intersect sits roughly 450 to 500 kilometers, about 280 to 310 miles, away from the planet's true center. That single offset is enough to warp the whole protective shell. And the place where the warp bites hardest, where the inner Van Allen belt sags down closest to the ground, happens to sit squarely over the South Atlantic, stretching from the coast of Brazil out towards southern Africa. Since its initial discovery in 1958, the anomaly's southern edge has stayed roughly fixed, while it has steadily expanded to the northwest, the north, the northeast, and the east. Think of Earth's magnetic field the way you'd think of a fitted sheet stretched over a mattress that isn't quite the shape it should be. Most of the sheet lies flat, tight, doing its job, but over one corner, the fitting is loose, the fabric sags, and whatever the sheet was supposed to keep off the mattress gets through. Over the South Atlantic, that sag brings the inner radiation belt down to an altitude of only roughly 200 kilometers, about 120 miles, above the surface, low enough to touch the orbits of hundreds of working satellites. And the sag is getting deeper. Data gathered by the European Space Agency's SWARM mission, a trio of satellites built purely to map Earth's magnetism with extraordinary precision, shows the anomaly's weak patch has expanded by an area nearly half the size of continental Europe since 2014 alone. In one narrow slice of that region, off the coast of southern Africa, the field has been weakening even faster than the rest of the anomaly since around 2020. Ground and satellite measurements together show the minimum field strength at the anomaly's core dropped by roughly 8% between 1970 and 2020, while at the same time the anomaly itself grew larger and crept westward at a pace of around 20 kilometers, about 12 miles, a year. Chris Finlay, a geophysicist at the Technical University of Denmark who works directly with the SWARM data, described what the satellites were showing in a way that should genuinely stop you. This isn't one smooth, uniform weakening. The anomaly isn't a single block. It's changing differently toward Africa than it is near South America, and there's something special happening in that region that's causing the field to weaken in a more intense way. Something inside the planet is not behaving the way a tidy, symmetrical magnet is supposed to behave. And when NASA geophysicist Weijia Kwang went looking for why, his explanation was stranger than a simple weak spot. He found that a localized patch of field with reversed polarity is growing strongly inside the anomaly region, dragging the local intensity down far below the strength of the surrounding field. Read that again slowly. Reversed polarity. Somewhere down in the churn, beneath the South Atlantic, a small patch of the field is pointing the wrong way compared to its neighbors. Like a tiny, rebellious corner of a bar magnet, that decided to flip itself around while the rest of the magnet stayed put. And in 2020, researchers noticed the anomaly's weakest core had started to do something even odder. It split. The region of minimum field strength divided into two separate lobes, creating fresh complications for every satellite mission trying to plan around it. One anomaly had quietly become two, drifting apart from each other beneath the ocean, each one its own small crack in the shield. Nobody watching the data could yet say why, only that whatever was driving the split lived far deeper than anyone had first suspected. What's causing this? Here, scientists are honest about the limits of what they know, and that honesty matters. One leading hypothesis points not to the core alone, but to something enormous, sitting at the boundary between the core and the mantle, thousands of kilometers down. A massive reservoir of unusually dense rock scientists call the African Large Low Shear Velocity Province, which may be disrupting the magnetic field generated just beneath it. It's a real, serious hypothesis, backed by seismic imaging of the deep Earth, but it's still a hypothesis, one candidate explanation among several, not a settled answer. And crucially, the agencies tracking all of this want you to hear the calm part just as clearly as the dramatic part. NASA has been direct that the anomaly creates no visible impact on daily life at the surface, and that its weakening intensity still falls within what scientists consider the bounds of normal variation. But the same agency is equally direct that recent observations and forecasts show the region continuing to expand westward and continuing to weaken. Not an emergency, not nothing either. A slow-moving, carefully monitored anomaly that keeps refusing to plateau. Down here on solid ground, none of this touches your life at all. You could stand in Sao Paulo or Cape Town right now and feel absolutely nothing. No headache, no static, no flicker of instruments in your pocket. This isn't a threat to people walking around under it. It's a threat to anything flying through it. And that is exactly where this story turns from a quiet geophysical curiosity into something with a body count of machines. Because while the anomaly over Brazil sits invisible and harmless to anyone standing beneath it, the moment something leaves the ground and climbs into orbit, it stops being invisible at all. And one particular satellite found that out the hard way, spinning itself apart in silence on the far side of the planet from anyone who could help. Every satellite that circles low over the South Atlantic has to cross through that weak patch eventually, and when it does, it stops flying through empty space and starts flying through weather, a storm of high-energy protons that the rest of its orbit simply doesn't have to deal with. The Hubble Space Telescope, one of the most carefully engineered spacecraft ever built, treats the anomaly the way a pilot treats a known patch of severe turbulence, not with panic, but with a strict, practiced routine. Hubble passes through the anomaly around 10 times a day, spending roughly 15% of its total orbital time inside it, and during each pass, ground controllers switch off its most sensitive instruments to keep stray radiation from corrupting the data. Even the cameras that stay on don't come through clean. Hubble's Wide Field Camera 3 can keep functioning through the anomaly, but the images it captures there still show a telltale speckling of radiation artifacts. Tiny scars of static left behind by particles slamming through the sensor, visible proof, baked right into some of the most beautiful images ever taken of deep space, that something down here on Earth reached up and touched them. In 2003, the European Space Agency's cluster mission, 4 spacecraft flying in formation specifically to study Earth's magnetosphere, crossing through the anomaly twice on every orbit, lost control of one satellite's onboard computer entirely. The spacecraft suffered a sudden, unexpected shutdown while passing through the anomaly, and engineers traced the failure directly back to a single event upset caused by radiation in that exact region. 4 years later, an entire commercial satellite fleet ran into the same wall. Globalstar, a company running a network of satellite phones, watched several of its first-generation spacecraft degrade and fail through 2007. The company lost several of its satellites that year, and the losses are believed to be tied to electronic components degrading from radiation damage picked up while passing through the anomaly. An industry analyst summed up the design flaw bluntly at the time. At that altitude, the radiation belts are extremely hazardous, and very few satellites are deliberately placed in that region because of it. An entire satellite phone network, degraded by an invisible patch of sky most of its customers had never heard of. And Globalstar, it would turn out, had gotten off comparatively easy. And then there is Hitomi. In February of 2016, Japan's space agency launched one of the most sophisticated X-ray observatories ever built, designed to study black holes and galaxy clusters with a precision no previous mission had matched. Weeks later, passing through the South Atlantic Anomaly, its star tracker, the instrument that tells a spacecraft which way it's pointed by locking onto known stars, began glitching. The star tracker suffered a series of glitches while crossing the anomaly, forcing the satellite to switch over to backup gyroscopic instruments, which then failed as well. Without a reliable sense of its own orientation, the spacecraft's automated systems appear to have tried to correct for a spin that wasn't actually happening, and in doing so, spun the satellite for real, faster and faster, until pieces began tearing away from the hull. The satellite was on the opposite side of Earth from Japan at the time, out of direct contact with mission control, and the error was only discovered once it was already too late to stop. A headline from that week summed up the loss in 6 blunt words. Japan's most powerful X-ray satellite is dead. A machine built over years, worth hundreds of millions of dollars, undone in minutes by a patch of weak magnetism most people will never fly over even once. Machines, at least, have the mercy of not knowing what's coming. The astronauts who fly through that same patch do not have that mercy, because unlike Hitomi's instruments, their eyes never get the option of switching off. The International Space Station doesn't get the option of simply switching itself off when it crosses the anomaly because there are people inside it. Orbiting at an inclination of 51.6 degrees, the station required extra shielding built directly into its design specifically to deal with this problem. And the astronauts inside that shielding have reported something that sounds, on first hearing, almost impossible. They can see the radiation. Not through a window, behind their own closed eyelids. Apollo astronauts, coasting through deep space far outside the protection of Earth's magnetic field entirely, began reporting strange flashes of light the moment they settled into the dark, dream-heavy quiet before sleep. In their reports, they described the flashes in 3 basic shapes: the spot, the streak, and the cloud. And nearly all of them were colorless, except for one, described by Apollo 15's commander David Scott, who saw something rarer, a flash he described as blue with a white cast, like a blue diamond. These weren't hallucinations, and they weren't dreams. They were the astronauts' own retinas being struck directly by cosmic particles too energetic for any wall of metal to fully stop. A front-row seat to radiation that, on the ground, none of us will ever consciously perceive. The rate of those flashes wasn't random either. It tracked the sky beneath the spacecraft with eerie precision. On Skylab, in low orbit, crew members recorded roughly 3 flash events per minute after around 17 minutes of dark adaptation during normal stretches of their orbit. But the moment the station crossed into the South Atlantic Anomaly, the frequency nearly tripled to about 9 events every minute, at an orbital altitude of 443 kilometers, roughly 275 miles. 9 flashes a minute. That's not a glitch in an instrument panel. That's a human eye, sealed inside a spacecraft, directly registering the shape of an invisible hole in the planet's shield as it passes underneath. This isn't some rare fluke experienced by 1 or 2 astronauts on one unlucky mission. Roughly 80% of astronauts surveyed have reported perceiving these flashes at least a few times during their missions, often across several orbits. Decades later, astronaut Don Pettit, who spent months at a time aboard the International Space Station, described his own version of the phenomenon in far gentler language than radiation exposure. In his crew logs and later talks, he described the flashes as resembling luminous, dancing fairies, and he noted they arrived more often whenever the station was crossing the South Atlantic Anomaly. Part of what he and others are seeing has a strange and genuinely elegant physical explanation. A charged particle moving through the fluid inside the eye, faster than light itself travels through that same fluid, emits a faint cone of blue light. the exact same physical effect that makes the water glow blue inside a nuclear reactor. Somewhere behind an astronaut's own eyelids, for a fraction of a second, the same physics that lights up a reactor core is quietly firing off. It looks beautiful in the telling. It is not harmless. Each heavy particle that tears through an astronaut's brain leaves behind a microscopic track of broken DNA and disrupted cell membranes. And over the course of a long mission, that same brain absorbs many thousands of these tracks, with the damage slowly accumulating. Dancing fairies and scar tissue from the very same invisible storm. Every flash behind those eyelids and every fried transistor before it traces back to the same fight happening in a place none of us will ever see with our own eyes. If a weak patch over Brazil can already switch off cameras on a 35-year-old space telescope, spin an X-ray observatory to pieces, and fire light directly into an astronaut's optic nerve from 30,000 feet and beyond, the obvious question is, what is actually driving it? And here is where the story gets bigger than one patch of sky over one ocean. Because the anomaly over the South Atlantic isn't the disease. It's a symptom, a visible bruise on the surface of something enormous happening far beneath it. Something that, at this very moment, is also responsible for dragging the entire magnetic North Pole across the Arctic Ocean at a pace with no precedent in recorded history. Down there, roughly 3,000 kilometers beneath your feet, an ocean of molten iron, the size of a planet, is doing something scientists have only recently caught in the act, something involving two enormous, competing patches of magnetism locked in what one researcher flatly called a tug of war. And right now, one of them is winning. That tug of war has a name now, location, and a timeline. And it explains something about the racing pole that should have been flatly impossible under the models scientists were using only a decade ago. Beneath the Canadian Arctic and beneath Siberia sit two enormous patches of magnetic flux, each one rooted deep at the boundary between Earth's molten outer core and the solid rock of the mantle above it. Nearly 3,000 kilometers, close to 1,900 miles, straight down. Geophysicists gave them a plain, almost boring name, lobes of flux. But what they found when they modeled them was anything but boring. A team led by Phil Livermore at the University of Leeds tracked these two lobes using decades of satellite and observatory data, and the pattern they found was stark. The Canadian lobe, which had been the stronger of the two for centuries, was steadily weakening and stretching thin. The Siberian lobe, meanwhile, was holding steady, even strengthening in places. The magnetic North Pole doesn't drift on its own. It sits, mathematically, at a kind of balance point between competing poles. And for 400 years, Canada's pole had simply been stronger. Once that balance started tipping, the pole had nowhere to go but toward whichever side was winning. Picture two teams locked in a tug-of-war over a rope, evenly matched for a very long time, the flag in the middle barely twitching year to year. Then, one team's grip starts slipping, not all at once, but steadily, rope burning through their palms a little more each season. The flag doesn't teleport to the other side, it accelerates toward it, faster and faster, the closer the losing team gets to letting go entirely. That is, almost exactly, what the pole has been doing since the 1990s. It isn't wandering aimlessly, it's being pulled, hard, by a fight happening in a place none of us will ever see with our own eyes. And the fight is not over. Livermore's team found that if the current trend holds, the pole's race toward Siberia should eventually slow down again, once the Siberian lobe's advantage stabilizes. Should. That word is doing a lot of work. Because the honest truth is that nobody fully understands why the Canadian lobe started losing its grip in the first place. To find that answer, you have to stop looking at maps of the surface entirely and go looking instead inside the ocean that's actually causing all of this. An ocean with no waves you could ever see, no shoreline, and no light of any kind. 3,000 kilometers beneath the ground you're standing on right now. Earth's outer core is a genuine ocean, just not one made of water. It's roughly 2,200 kilometers, about 1,400 miles, of molten iron and nickel, wrapped around a solid inner core the size of the moon, and it never sits still. Heat leaking outward from that solid inner core, plus the planet's own rotation, keeps the liquid metal churning in slow, colossal loops, rising, cooling, sinking, all of it twisted and dragged sideways by the Coriolis effect, the same rotational force that spins hurricanes on the surface far above. That churning liquid metal is an electrical conductor, and a moving conductor dragged through a magnetic field generates electric currents, and those currents generate more magnetic field, which then gets dragged around by more moving metal, feeding itself in an endless loop. Scientists call the whole self-sustaining machine the geodynamo. It has been running, without ever fully switching off, for roughly the last 3.5 billion years. And it is the entire reason Earth has a magnetic field at all. Here's the detail that should reframe everything you just heard about the pole and the anomaly. That iron ocean doesn't just churn in slow, even loops, like a pot of soup on a stove. It has currents inside it that move fast, startlingly fast by the standards of anything happening inside solid rock. Beneath Alaska and Western Canada, researchers using data from the European Space Agency's swarm satellites identified a distinct jet of liquid iron, a ribbon of fast-moving molten metal snaking along the top of the outer core, and it had picked up speed dramatically. Between 1999 and 2007, this jet, sometimes described as an underground river of liquid iron, roughly tripled its flow rate, reaching speeds of around 40 to 45 kilometers, roughly 25 to 28 miles, a year. That sounds slow compared to a car or even a bicycle. It is anything but slow compared to solid rock, which typically creeps along at a pace closer to a fraction of an inch per year. Imagine a river that, for your entire life, moves at the speed of a dripping faucet, and then, one decade, without warning, starts running like a mountain stream. Something pushed that jet stream of iron into overdrive, right around the same stretch of years when the magnetic pole itself started sprinting. And the core doesn't just accelerate smoothly either, it jolts. Geophysicists have a term for these sudden lurches in the field's behavior: geomagnetic jerks, abrupt changes in how fast the field's intensity is shifting, as if something deep down briefly stumbled. One of the clearest jerks on record hit in 2016, and when researchers went looking for its source, they traced it to a sudden pulse originating almost directly beneath South America, the same general region sitting under the weakest, most rapidly splitting patch of shield on the entire planet. One leading explanation involves something called a hydromagnetic wave, essentially a ripple of magnetic tension traveling through the liquid core, the way a plucked guitar string sends a wave down its own length. Except this wave travels through molten metal instead of steel, and instead of taking a fraction of a second, it can take years to cross the core and surface as a jerk in the field above. A ripple, plucked somewhere in the depths, arriving at the surface as a stumble in the compass. None of this is happening in some other disconnected part of the planet. It's happening directly beneath the anomaly, directly beneath the racing pole, in the same iron ocean, on the same restless timetable. And here is the question that should be sitting uncomfortably with you right now. If a jet of liquid metal can triple its speed in less than a decade, and a wave rippling through molten iron can trigger a sudden jerk in the field detectable from orbit, what happens if these disturbances don't stay small? What happens if the field doesn't just weaken in patches and wobble at the poles, but actually starts to come apart at a global scale? Because there is a name for exactly that scenario, and it has already happened before, more than once, written directly into the rock beneath your feet. Earth's magnetic field, taken as a whole, has been losing strength for a long time, not just in the anomaly, but everywhere, on average, for roughly the entire span of recorded measurements. Since scientists started keeping systematic records in the 1840s, the field's overall strength, technically called the dipole moment, has dropped by around 9 to 10%. That number on its own sounds almost reassuring. A gentle decline, spread across nearly 2 centuries, hardly the stuff of catastrophe. But recent readings complicate that comfort considerably. Over just the past 2 decades, the rate of weakening in and around the South Atlantic Anomaly has been running at roughly 5 times faster than the global average pace recorded over the previous century and a half. The overall field is fading slowly. The wound over Brazil is fading fast. So the question every geophysicist eventually gets asked, usually with a slightly nervous laugh attached, is simple. Is this the start of a flip? Is the compass about to point south? The honest answer is that Earth's magnetic poles absolutely have flipped before, completely, and there is no serious scientific dispute about that fact. It's written directly into the magnetic stripes, frozen into the sea floor on either side of the mid-ocean ridges, alternating bands of reversed polarity, laid down like rings in a tree, one flip after another, stretching back hundreds of millions of years. A full reversal, where North and South genuinely trade places for good, is a real, repeatedly documented event in Earth's deep past. But full reversals are rare on any timescale a human mind can comfortably hold. The current orientation of the field has held steady for around 780,000 years, an almost incomprehensible stretch of time. And when reversals do happen, they typically unfold over 1,000 to 10,000 years, not overnight, not even within a single human lifetime. There is, however, a stranger and more relevant cousin of the full reversal called an excursion, a brief, dramatic wobble where the field weakens severely, drifts wildly, sometimes even partially flips, and then snaps back to where it started, all without completing a full, permanent reversal. The best documented example is called the Le Champ event, dated to roughly 41,000 years ago, discovered originally in volcanic rock in France, and later confirmed in ice cores from Greenland and Antarctica. During the Le Champ event, the field's strength collapsed to somewhere around 5% of its modern value, and the magnetic poles swung wildly, possibly tipping most of the way toward a full reversal before pulling back. And this is the detail that should genuinely stop you. Researchers reconstructing this event from ice core radiation markers found that the whole dramatic episode, from collapse to recovery, unfolded over roughly 250 years. A geological blink, but a span of time that would have swallowed several full human generations, living their entire lives under a shield, running at a small fraction of its normal strength, exposed to sharply elevated radiation from space, and a far more violent, far more widespread aurora than anything visible today. Which leaves exactly one question hanging in the air. Are we watching the early minutes of that same kind of event unfold right now? Scientists are careful, and rightly so, not to answer that question with false confidence in either direction. The current weakening, even in its most aggressive patches, is nowhere near the near-total collapse recorded during the Le Champ event. NASA's own public guidance is blunt about the timescale mismatch. Variations in the field, even fairly dramatic regional ones like the anomaly, are considered part of the normal, ongoing behavior of a dynamic magnetic system, not necessarily the leading edge of an imminent reversal. But not necessarily is not the same as definitely not. The honest scientific position sits in an uncomfortable middle. This could be ordinary secular variation, the kind of drift and wobble the field has always shown across centuries, or it could be the opening chapter of a much longer, slower transition that won't fully reveal itself for decades or centuries yet. Nobody currently monitoring this field, with the tools available today, can tell you with certainty which one it is. What they can tell you, with total certainty, is that whichever one it turns out to be, the machinery riding on top of that field down here on the surface is already having to answer for it. And one particular piece of that machinery has almost no meaningful insurance policy against the worst version of this story. The power grid that keeps your lights on, your refrigerator humming, your hospital's ventilators running, was built almost entirely by engineers who were solving for storms, floods, ice, and heat, not for storms arriving from 93 million miles away. And yet the grid has already been struck hard by exactly that kind of storm, more than once, and the mechanism is disturbingly direct. When the sun launches a coronal mass ejection, a billion-ton cloud of magnetized plasma blasted outward from the solar surface, and that cloud happens to be aimed at Earth, it slams into our planet's magnetic field and sets the whole system ringing like a struck bell. That ringing field, in turn, induces electrical currents in anything long, metallic, and grounded on the surface below. And nothing on Earth is longer, more metallic, or more thoroughly grounded than a continental power grid strung across thousands of kilometers of transmission lines. Engineers call these unwanted currents geomagnetically induced currents, and the transformers sitting at the heart of every major substation were never designed to handle them. A transformer expects a clean, oscillating current, flowing back and forth in a steady rhythm. A geomagnetically induced current behaves more like direct current shoved sideways into that system, and it can push the transformer's magnetic core into a state called saturation, essentially overloading it, forcing it to run wildly outside its intended operating range, generating heat where there shouldn't be heat, and in the worst cases, destroying the transformer outright. Engineers had a name and a model for this exact failure mode. What they didn't have, on one ordinary night in March of 1989, was enough warning. This has already happened, on a scale large enough to blur an entire province off the map. On the 13th of March, 1989, a severe geomagnetic storm struck Earth, and within about 90 seconds, protective relays across Hydro-Quebec's power grid began tripping in a rapid, cascading sequence. The entire province of Quebec, home to roughly 6 million people, lost electricity, and the blackout lasted approximately 9 hours before power could be fully restored. 9 hours. In March, with hospitals running on backup generators and families sitting in the dark not entirely sure why. That event happened at a moderate storm strength, nowhere close to the most extreme geomagnetic storm humanity has clear historical evidence for. That more extreme benchmark has a name, the Carrington event, a colossal solar storm that struck Earth in early September of 1859, so intense that telegraph operators across Europe and North America reported their equipment sparking, their paper tape catching fire, and some operators finding they could disconnect their batteries entirely and keep sending messages purely on the current the storm itself was inducing in the wires. Auroras during that storm were reported as far south as the Caribbean, vivid enough that people in some locations could read a newspaper by their light in the middle of the night. Modern infrastructure has never been tested by a storm of that exact magnitude, and that absence of a direct hit is not a comfort, it's a blind spot. A widely cited 2013 risk assessment from the insurance market, Lloyd's of London, working alongside the space weather analytics firm Atmospheric and Environmental Research, estimated that a Carrington-scale storm striking the modern United States could leave between 20 million and 40 million people without power, for a recovery period that could stretch from 16 days up to as long as 1 to 2 years in the hardest-hit regions, driven largely by the fact that large, custom-built transformers, the kind capable of failing outright in a severe storm, can take many months to manufacture and replace, because spares are not typically sitting on a shelf waiting. That worst-case scenario has never actually struck the modern grid dead-on, but in 2012, it came close enough to make solar physicists' blood run cold. We have already had a warning shot that came within a hair of testing that exact scenario for real. On the 23rd of July, 2012, a coronal mass ejection erupted from the Sun with a velocity and intensity that solar physicists compared directly to the Carrington event, and it crossed the exact orbital point where Earth would have been, missing our planet only because it launched about 1 week before Earth arrived at that point in its orbit. Daniel Baker, a space weather researcher at the University of Colorado who studied the event closely, put the stakes in about as stark a sentence as any scientist offers publicly. If it had hit, we would still be picking up the pieces. 1 week. That is the entire margin on our current understanding between a fascinating case study for solar physicists and a continental-scale blackout event unlike anything the modern grid has ever had to survive. And the shield that failed to stop the last close call isn't getting any stronger while we wait for the next one. And the grid is only the loudest, most visible piece of infrastructure sitting exposed under this thinning roof. Up above the transformers and the transmission towers, in the thin, cold air where commercial aircraft cruise, and where astronauts orbit for months at a stretch, an entirely different set of consequences has already been unfolding, quietly, largely out of public view, involving radio blackouts that have gone completely silent mid-flight over the poles, a magnetic flip that computer models still cannot reliably predict even a few decades out, and a growing question about what it actually means for the rest of us to keep living, working, and flying underneath a shield that keeps changing shape while nobody down here can feel it happen. The passengers on that flight had no idea anything was wrong. They were somewhere over the Arctic Ocean, tracking one of the great circle routes airlines use to shave hours off a journey between North America and Asia, cutting straight across the top of the world instead of arcing around it. Down in economy, people were watching movies, sleeping under thin blankets, completely unaware that up in the cockpit and in a control room thousands of kilometers away, a very old and very reliable form of communication had just gone completely dead. High-frequency radio has been the backbone of polar aviation for decades, precisely because satellite coverage and ground-based radar both fall apart the closer you get to the poles. Over the middle of an ocean, or the emptiness of the high Arctic, there's often no radar tracking a plane's position at all. Separation between aircraft depends on pilots and controllers staying in voice contact, reporting positions, confirming altitudes, the same basic principle aviation has relied on since the propeller age. In May of 2024, during the most severe geomagnetic storm to strike Earth in more than 20 years, that entire communication layer went silent across huge stretches of the polar cap at once. Airlines, including Finnair and Air France, responded by shifting some of their transpolar and high-latitude routes further south, trading a longer flight time for a communication link that would actually keep working. The physics behind that blackout has nothing to do with weather in the ordinary sense, and everything to do with the same magnetic architecture we've been tracing this entire time. And the reason that architecture fails so completely right at the poles comes down to a piece of geometry most passengers never think to ask about. Earth's magnetic field doesn't wrap the planet in one smooth, closed bubble. Near the poles, the field lines don't loop back down to the surface. They open directly outward into space, like the neck of a funnel standing straight up out of a bowl. That open geometry is a feature, not a flaw. It's part of how the field has always worked. But it means the poles are where the shield was always thinnest by design. The place where particles streaming from the sun get funneled straight down into the upper atmosphere instead of being deflected around it. During a strong solar event, that funnel fills with energetic particles fast enough to ionize a thick layer of the atmosphere across the entire polar cap. And high-frequency radio waves, which depend on bouncing cleanly off a stable ionosphere, simply stop bouncing. Pilots don't hear static, they hear nothing at all. NOAA's Space Weather Prediction Center tracks this exact hazard the same way the National Weather Service tracks a hurricane, issuing a formal warning specifically for what's called a polar cap absorption event, rated on its own severity scale, precisely because commercial aviation depends on knowing when the funnel is overflowing. During the most extreme instance on record, tied to a series of solar storms in October and November of 2003, radio blackouts across the polar regions ran so severe and so prolonged that some transpolar flights were diverted to lower latitude routes for days at a stretch, and airlines reported having to fall back on backup communication procedures across parts of the Arctic. And here is the detail that connects this directly back to the racing pole we started with. The funnel doesn't sit in a fixed spot on the map. It's centered on the magnetic pole, not the geographic one, which means as that pole keeps sprinting towards Siberia, the exact air corridors most exposed to this kind of blackout are quietly shifting too, moving underneath flight paths that were mapped and considered safe based on where the pole used to be. There's a second, quieter cost riding on the same planes, one that has nothing to do with radios at all. At cruising altitude, 35,000 feet or so, roughly 10 or 11 kilometers up, the atmosphere overhead is already thin enough that it stops blocking a meaningful share of cosmic radiation, and the magnetic funnel over the poles offers noticeably less deflection than the field does at the equator. Flight crews working regular transpolar and high-latitude routes accumulate a measurably higher radiation dose over a career than crews flying tropical routes at the same altitude, high enough that several countries, under aviation and radiation safety regulations, formally classify aircrew as occupationally exposed workers and require their cumulative dose to be monitored, the same basic category used for people who work around medical X-ray equipment or nuclear facilities. During a major solar particle event, that background dose can spike sharply for the length of a single flight. None of this makes ordinary air travel dangerous for the people sitting in seat 14A, with a window view of the ice below. It does mean an entire professional workforce has quietly been added to the list of people whose jobs put them in closer contact with the weakening shield than the rest of us will ever notice. And it raises an obvious next question. If the pole keeps moving, if the funnel keeps drifting, and if the field beneath it all keeps fading in patches, how far does this actually go? Is there a model, anywhere, that can tell us where this ends and when? In 1995, two geophysicists named Gary Glatzmeyer and Paul Roberts did something nobody had managed before. They built a three-dimensional computer simulation of Earth's outer core, obeying the real physical laws of fluid motion, heat, and electromagnetism, and let it run. The simulation didn't just produce a stable Earth-like magnetic field. Left running long enough, it spontaneously flipped, entirely on its own, with no outside nudge required, producing a reversal that looked remarkably similar to the ones recorded in real seafloor rock. It was a landmark result. It proved that reversals aren't some exotic external event requiring an asteroid strike or a passing star. They're simply what a planetary dynamo does on its own, given enough time, purely from its own internal churn. But here is the part that quietly undercuts any hope of a forecast. That same simulation, and every serious one built since, is exquisitely sensitive to its own starting conditions. Change the initial temperature of the core by an amount too small to even measure in reality, and the simulated field will still eventually flip, just at a wildly different point in simulated time, sometimes off by tens of thousands of years, for a change too tiny to detect with any instrument we currently have access to inside the real Earth. That is the exact same property that makes weather forecasting reliable for 5 days and nearly worthless for 5 months. Meteorologists can tell you with real confidence whether it will rain this Thursday. Ask them to guarantee the weather on a specific afternoon 2 years from now, and the honest answer is that the atmosphere itself doesn't preserve that kind of certainty long enough for anyone to promise it. The core is the same story, just playing out across thousands of years instead of days. Geophysicists can run the physics forward and watch reversals emerge naturally from the model. They cannot run the physics forward on the real planet and read off a date, because the real planet's exact internal state, right now, this second, simply isn't known, with anywhere near the precision that kind of prediction would require. That doesn't mean scientists are simply guessing in the dark, though. And one geomagnetist who has spent her career reading the planet's deep past has already told us plainly which side of that uncertainty she leans toward. What they can do is watch the signs on the surface, the same way a geologist watches a swelling volcano without being able to promise the exact hour of an eruption. Catherine Constable, a geomagnetist at the University of California, San Diego, who has spent years reconstructing the field's past behavior from volcanic rock and sediment cores, has pointed out that the current rate of overall weakening, even including the anomaly's accelerated patch, still sits well within the range of ordinary ups and downs the field has shown repeatedly over the last several thousand years, behavior recorded clearly in the paleomagnetic record long before any reversal actually followed. Weakenings like this have happened before, more than once, and simply faded back out without ever tipping into a full flip. That's the calming half of the picture. The unsettling half is that researchers cannot rule out the other option either, that this is the early, barely perceptible opening act of something that won't fully show its hand for another few hundred years, long after everyone currently studying it and everyone currently watching this video is gone. Both possibilities remain live. Neither can currently be eliminated. And that gap between what the data shows right now and what it will eventually turn into is exactly the space where satellites, airlines, and power grid engineers are all being forced to make real decisions today, using an incomplete picture of a system that took 3.5 billion years to build and doesn't much care how inconvenient its timeline is for us. So where does that actually leave us? Not scientists in a lab in Denmark or California, but ordinary people, living, flying, and building things under a shield that keeps quietly rearranging itself overhead. It leaves us in a strange, genuinely unusual position in the story of our species. For nearly the entire time humans have existed, this field was simply a fact of life, as fixed and unremarkable as gravity, noticed only by the rare person clever enough to build a compass and wonder why the needle behaved the way it did. We are the first generation equipped to actually watch it change in something close to real time. A trio of European satellites circling overhead every single day, logging its shape down to fractions of a percent, catching a patch splitting in two, catching a jet of molten iron tripling its speed, catching a pole crossing the Arctic Ocean fast enough to force mapmakers to tear up their own schedule. That's an extraordinary position to be in, and it comes with an extraordinary temptation to panic, which is exactly the wrong response, and not what the evidence supports. Let's be precise about where things actually stand, because precision is the one thing this topic desperately needs and rarely gets. The South Atlantic Anomaly is real, it is deepening, and it is splitting into separate lobes. But NASA's own public assessment is that it poses no direct danger to anyone on the ground, and that its most severe practical consequence is the extra radiation shielding and operational caution required for the satellites and spacecraft that happen to pass through it. The magnetic pole really is racing toward Siberia at a pace with no precedent in 4 centuries of measurement, but current modeling suggests that race may already be slowing, as the tug of war between the 2 great flux lobes beneath the Arctic settles toward a new, if different, balance. The overall field really has weakened by something close to 9 or 10% since the 1840s, but that number sits comfortably inside the range of natural variation the field has demonstrated repeatedly across recorded history, according to researchers who study its longer past. Every alarming thread in this story is real. None of them currently rises to the level of an emergency. That distinction matters, and it's worth being honest about it, even when the honest version is less dramatic than the headline. What has genuinely changed, and what does deserve real attention rather than alarm, is how much of modern life now sits directly in the path of consequences this field used to absorb quietly on our behalf. A century ago, a geomagnetic storm was little more than a spectacular light show. Auroras dipping unusually far south, telegraph operators occasionally startled by sparking equipment, and almost nothing else. Today, that same storm threatens satellite constellations that carry global positioning signals, weather forecasts, and financial transaction timing. It threatens transformers that took months to manufacture and can take just as long to replace if they fail all at once across a region. It threatens communication links carrying commercial flights across the one part of the globe where there's no backup radar to fall back on. We built an entire layer of civilization on top of an assumption of magnetic stability that the planet itself never actually promised us. The shield was never a wall. It was always a living, churning, occasionally unstable ocean of molten iron, doing its best. And it has been doing that job for something like 3.5 billion years, long before there was a single satellite, transformer, or airplane depending on it to hold steady. Agencies around the world are watching this with the seriousness it deserves, without treating it as a crisis. The European Space Agency's Swarm mission keeps mapping the field's shape month after month, feeding data straight into the models that airlines, satellite operators, and grid engineers actually rely on. NOAA's Space Weather Prediction Center issues its geomagnetic storm warnings on a graded scale, from a minor G1 up to an extreme G5, the same practical plain language approach used for hurricanes, precisely so the people who need to act on a warning don't have to first decode a research paper to understand it. The World Magnetic Model, the one baked into your phone's compass app right now, gets checked and rebuilt on a fixed schedule specifically because everyone involved already knows the pole doesn't hold still long enough to trust an old chart indefinitely. None of that is the behavior of institutions bracing for imminent catastrophe. It's the behavior of institutions that have learned, the hard way, through one dead X-ray telescope and one 9-hour blackout across an entire Canadian province, that a moving target deserves to be tracked closely rather than assumed. Go back for a moment to that compass needle sailors trusted centuries ago, the one they punished a man for eating garlic near, rather than believe the instrument itself might simply be following a truth stranger than anyone on deck was prepared to accept. The needle was never broken. It was doing exactly what it has always done, pointing, faithfully, at wherever the deep, restless iron ocean beneath our feet happens to be leaning at that particular moment in its 3.5 billion year life. We just finally have the instruments, the satellites, and the patience to notice it, leaning further and faster than it has in living memory. The anomaly over Brazil keeps widening. The pole keeps running, even if it's easing its pace. The iron ocean beneath it all keeps churning, indifferent to airline schedules and insurance actuaries and the phone compass in your pocket that quietly recalibrates itself every time you open a map. We don't know yet whether this is the field's ordinary breathing or the first slow inhale of something that won't fully exhale for another 1,000 years. Nobody currently alive will get to read the end of that particular chapter, but we get to watch it being written in real time, one satellite pass and one polar flight and one ground station reading at a time. And for a shield that spent billions of years going almost entirely unnoticed, that alone is worth paying attention to.